The following past paper question reads that when gaseous iodine is heated with hydrogen at 450 degrees centigrade, an equilibrium is established. And the equation is given: hydrogen and iodine gas are in equilibrium with HI gas. So the enthalpy change is also given. Now the question says which change of conditions will cause the purple color of the equilibrium mixture to become paler, which means that the purple color of the mixture becomes paler only if there's more forward reaction. There's less purple color being produced, more forward reaction, the purple color disappears. So basically you want the equilibrium to shift to the right to make it more colorless or more paler. So we're looking for conditions which are going to do that. Now the first one is decrease in pressure, and there's another option C, which is increase in pressure. Now remember that when you decrease pressure, equilibrium would favors the side with more gas moles. With more gas moles. Now the problem in this case is that there are two molecules, 2 moles of HI in the product side, and there's 1 plus 2 moles of reactants as well. So the moles of gas on both sides, on the reactant side and on the product side, is exactly the same. So changing pressure is not going to have any effect whatsoever, and the same is true for this, for option C as well. Increasing or decreasing pressure is not going to have any effect. Now if you look at option B, it talks about decreasing temperature. When you decrease temperature, then exothermic reactions are favored. By decreasing temperature. And if you look at the enthalpy change, it's given for the forward reaction, it's plus, which means it's endothermic. So the forward reaction is endothermic. So this arrow represents an endothermic change, whereas the other arrow, the backward reaction, would be the opposite. It's going to be exothermic. So if you decrease temperature, an exothermic reaction is favored. So backward reaction, the exothermic reaction would be favored, and more purple color would be produced. So this option also looks to be incorrect. And the last option is increasing temperature. If you increase temperature, then vice versa, endothermic reaction is favored. And in the above reaction, endothermic change is the forward reaction. It's plus 53, so forward reaction would be favored, and the mixture would become more colorless. So forward reaction would be favored. So option D is going to be your correct option for this question. The dimer X is stable when solid, but a dynamic equilibrium is set up in solution. So there's a dynamic equilibrium that is established where X is in equilibrium with Y. So X is getting converted to Y and vice versa. So I've written that down over here as well. X getting converted to Y and Y vice versa, converting back into X. And then the question reads that a solution of X has an initial concentration of 0.5 mole per decimeter cube. So that's your initial concentration of X, and when equilibrium is reached, the concentration of X has fallen down to 0.25 mole per decimeter cube. So I've written this down over here. The initial concentration of X is 0.5 mole per decimeter cube, and once equilibrium has been reached, it falls down to 0.25 mole per decimeter cube. So there's a difference now. That's 0.25 is now missing, which basically means that 0.25 mole per decimeter cube of X has reacted because 0.25 is missing now. So at equilibrium you only have 0.25. So if 0.25 reacted or is gone missing or gets used up, that means that 1X produces 2Y. So according to this ratio, if 0.25 reacted, that means 1:2 means that 0.5 mole per decimeter cube of Y would be produced according to the same ratio. So 0.5 mole per decimeter cube of Y is produced. So at equilibrium, initially you had 0 moles of Y, and once 0.25 moles of X reacted, then 0.5 mole per decimeter cube of Y would be produced. So these are my equilibrium moles which I now have with me. And the next thing I need to do is the question states that the changes in X and Y are plotted against time until equilibrium is reached. The value of Kc has been calculated. So the answer basically wants you to calculate the value of Kc. We need to first give the expression for Kc, which in this case is going to be the concentration of products divided by the concentration of reactants. So it's going to be Y squared divided by X squared. So the concentration of Y squared divided by the concentration of X, and that would be raised to the power 1. The reason why we are squaring it is because the coefficient of Y is 2. I'm going to substitute the values now. So it's going to be 0.5 squared, which is 0.25 divided by 0.25. And the value of Kc that I get is going to be equal to 1. So if you look at all the options, so it's either going to be option A, because in A the value of Kc is given as 1. Or it could also be, if you look at the other option, it could also be C, because the value of Kc over there is also given as 1. So C is also a possible candidate. B and D cannot be correct because in those cases the value of Kc is given as 2. So that's the first part. Now we have to figure out what the graph, which graph is correct. Now the concentration of X falls from 0.5 to 0.25, whereas the concentration of Y, which was initially 0, changes to 0.5 eventually. So the final concentration of X is 0.25 and the final concentration of Y is 0.5. So according to this, graph C looks correct because Y is initially 0 and then it rises to 0.5, and similarly X had an initial concentration of 0.5 and it falls to 0.25. So this is the point where equilibrium has been reached and the concentration of X and Y, they become constant. So option C is going to be your correct answer because the graph is correct as well as the value of Kc calculated is also correct.